Hello and welcome to the section of the Circuit Analysis Tutor. Here we're going to tackle this problem we have on the board. We have a 100 volt source, we have a 20 volt source, we have lots of 4 ohm resistors scattered everywhere. Here we have a voltage controlled voltage source. The value of this source is equal to the value that lies across that 4 ohm resistor down there. So we have a mixture of independent sources and also dependent source. And this entire circuit here, whatever it's doing, is driving this load. So across terminal A and B, it's driving a load resistance R. And the question is that you'd be asked on an exam or a quiz, what value of this resistance do we need to choose to make sure that maximum power is being transferred from this circuit to this load resistance, right? Obviously we learned if we choose 0 ohms, if we choose infinity ohms, we're going to get no power transferred in either case. So somewhere in the middle lies a perfect value, and that perfect value that results in maximum power transfer is simply chosen when we choose the value of this resistance to be equal to the Thevenin resistance of the rest of this circuit. And now you see why we spent so much time on Thevenin equivalent, because you use them, just for their own use, but then you also use them for things like this, maximum power transfer. You have to know on an exam that if you didn't know that it was involving the Thevenin equivalent, you wouldn't know what to do at all. But you have to know, okay, I need to go calculate the Thevenin resistance. How do I do that? How do I calculate the Thevenin resistance? Well, remember, there's several ways to do it, okay? In this circuit, we have a dependent source, so it kind of limits your options a little bit. There's really still a couple of ways you do it. You could find the open circuit voltage, the Thevenin voltage, and then you could find the short circuit current going through. So you could for instance, take this resistor out of the equation and expose terminals A and B. You could find the Thevenin voltage, you could find the short circuit current, and then you divide the two, and that would give you the Thevenin resistance of the remainder of the circuit looking back. But that's kind of a pain because, you have to take away this guy, and then you have to do kind of some mesh equations to do the Thevenin voltage, and then you'd have to short circuit it, and then you'd have to do find the short circuit current, which would be another set of equations that you have to solve. And then you get those two numbers and you divide them. So it's bulletproof, it's just a little bit of work. Another way that we can do it, that we talked about when we have these sources like that, is we can eliminate the independent sources. So this is a voltage source, and this is a voltage source. Since they're voltage sources, we can short circuit them, kind of eliminate them. We can't eliminate these guys, you can't eliminate the dependent sources, but we can get rid of these. And then we can hook up a test current, right, a test signal to the terminals and drive it with a known current. And then we can calculate the voltage that falls across that current source that we hook up out there. And as we talked about before when we did these Thevenin equivalent problems, by getting the ratio of the voltage drop across a known test current, you're basically calculating the resistance of the Thevenin resistance of the circuit as a whole as it behaves. So that's what we're going to do here, because you only have to solve one set of equations to get the Thevenin resistance. Remember, the question is, what value of R results in maximum power transfer? All you care about finding is the Thevenin resistance. You don't need to know the Thevenin voltage because you're not asked for that. You're only asked for this. So let's start by redrawing the circuit. We're going to short circuit these two guys, and we're going to hook a test current over here. So what we'll do is scoot over to this board here and do that now. Now we still have the dependent source from the top. So let me go ahead and hook this up. You're still going to have this resistance here. You're still going to have a resistance that falls under it, and a resistance that falls under there. Now when you get down here, you're going to short circuit this guy, so it's going to be gone. And then when you get here, you're still going to have this resistance, but there is a source here. You're going to short circuit that source. And then over here is where our load resistance usually is. We're going to hook up a test source. I like to use current sources, so I'm going to hook up a 1 amp source. And you can just label this terminal A and label this terminal B. Now let's go ahead and do some more labeling here. So everything here is pretty much 4 ohms. So this is 4 ohms, this is 4 ohms, this is 4 ohms, this is 4 ohms. Now the voltage V1 is across here, this is minus plus, and this is V1. So here we have quickly redrawn the circuit. And that's actually a good example. A lot of students, they'll skip a step of redrawing a circuit. They'll start scribbling on top of their original drawing, original circuit, to try to save time. You see, it only took less than 1 minute to probably draw this circuit, and now you have a clean drawing that's not cluttered and it's simplified. So make sure you do that. So here is our circuit. We have a test source here. Don't forget what we're trying to do. We're trying to find the Thevenin resistance of this circuit that lies over here. So we hook up a test source, and when you do that, a voltage is going to appear across that test source. We want to find out what the voltage across this source is. That's VAB, right? And by knowing that R is equal to V over I being the test current, then we can calculate the resistance of the circuit that lies over here. We studied that when we did Thevenin equivalent circuits, and I showed you how to use the test current method. All right, so let's go around and actually solve this guy. So what we have is, this is mesh I1, this is mesh I sub 2, this is mesh I sub 3. So we have 3 meshes, not too bad, not like a huge system of equations or anything. So let's just go methodically around mesh 1 and start writing equations. So going through this resistor, it's going to be I1 minus I2 times 4. That's the IR drop across this guy. And then when we get down here, you want to kind of ignore V1 for now. We'll get to that in a little bit. What you're going to have is I1 minus I3 times 4. That's the voltage drop across that. And then you're going to set that equal to 0. All right, so let's go and do some expanding here. So we'll have 4I sub 1 minus 4I sub 2 plus 4I sub 1 minus 4I sub 3 is equal to 0. Let's collect terms. 4 plus 4 is 8I sub 1 minus 4I sub 2 minus 4I sub 3, and that's equal to 0. Now we've done about as much as we can with mesh 1, so what I want to do is sort of stop here for a second, and I want to go work on mesh 3. Normally I, of course, write equations in order, mesh 1, mesh 2, mesh 3. But in this case, it's just irresistible because I know that mesh 3 is sharing a boundary with a known current source. So what I know is that I sub 3 is equal to -1, and that's why I like to choose current sources when I put a test current here, because since I'm using mesh current method all the time, it makes it very easy. Since this arrow is going opposite of this arrow, I have a negative sign. Now the reason I skipped over to do I sub 3 is because, you see, I don't have to do that, but I notice that I have this equation in terms of I1, I2, and I3. This is such a simple substitution, I'm going to plug this in now. Right? You don't have to do this, but I think it's worthwhile to just do it now. So what you're going to have is 8 times I1 minus 4 times I2 minus 4. Now I3 we're saying is -1 is equal to 0. So you have 8 I1 minus 4 I2. This is a positive 4, but I'm going to move it to the other side and make it a -4 because I want all my constants to lie on the right-hand side. So this is what I call a keeper equation. One of my final equations that I'm going to actually use to solve because I've simplified down. So I use mesh 1 to get this. I use mesh 3, which is so simply trivial, just to simplify things a little bit. All right, now let me scoot this board over here. And what we're going to do next is continue working. We're going to start working with mesh 2 now because we haven't even touched mesh 2. All right, now what we want to do now, since we've gotten mesh 1 taken care of, is we want to go off to mesh 2. So as we walk through this 4 ohm resistor, it's going to be I2 minus I1 times 4. So we're working on mesh 2. It's going to be I2 minus I1 times 4. And then when we get up to this source, we're going from negative to positive. So it's not a voltage drop, that's a voltage rise. So we treat that as a minus V1. And then when we get to the 4 ohm resistor, it's just I2 times 4. So that's a plus I2 times 4. And then when we get down to this 4 ohm resistor, it's I2 minus I3. So I2 minus I3 times 4. And all of that's equal to 0. So that's our equation. But we see here we have a couple things. First of all, we have I3. We know from before, so I'll do this. And we know that I3 is -1. So we know we can plug that in just a second. The other thing is we've introduced this voltage V1 running around. But when you look over here, V1 is defined to be the voltage drop across this 4 ohm resistor. And we know what that is because that's going to be equal to I1 minus I3 times 4. Notice the polarity from positive to negative, so we have to do it. I1 is going down, I3 is fighting it, so it's I1 minus I3 times 4. So what we figured out is V1 is equal to I1 minus I3 times 4. So let's go ahead and distribute this in. V1 is equal to 4 times I1 minus 4 times I3, right? But we just said we know what I3 is equal to. So really V1 is 4I1 minus 4 times negative 1, because that's what that's equal to. So V1 is 4I1 plus 4, right? So we're doing all this stuff just to save us a little bit of heartache later. We know now what V1 is equal to. We already knew what this was equal to. Let's take both of them and plug them in here. And when we do that, we should end up with a nice equation that gels well with the equation that we already wrote, and we'll be able to solve the whole thing. So let's go ahead and plug that in right now. All right, so what we're going to have when you distribute this in, it's going to be 4 times I sub 2 minus 4 times I sub 1 minus V1 is defined to be 4I1 plus 4 plus, this is going to be 4 times I2 plus, this guy, let's just go ahead and leave it kind of alone for just a second. We'll put the 4 out front and we'll say I2 minus I3, but I3 we know to be negative 1 equals 0. So we've substituted in for everything we know, and over here, let's just note, instead of writing the whole thing out, this is equal to 4I2 plus 4. This becomes a plus 1, so you multiply and you get this here. So when you take your time and you collect all of the terms, then for I1, what you have is negative 4I1 here and negative 4I1 here. So you have negative 8I sub 1. And for I2, you have 4 plus another 4. So that's going to give you 12I sub 2. All right. Now when you think about it, here you have a negative 4 here, and over here you have a positive 4, so that's just 0. So that's 0. So you've accounted for all the terms. We're adding up all the I1s and all the I2s, and we arrive at this equation here. So this is an asterisk equation. Now notice what we have. We have an equation in I1 and I2 here, and we have an equation in I1 and I2 here. And that's all we need because we already know what I3 is equal to. It's equal to negative 1. So let's go ahead and finish this problem up over here. And let's remind you quickly what the system is. The system that we've written down, just to remind you, is 8 times I1 minus 4 times I2 is negative 4. And negative 8 I1 plus 12 I2 is equal to 0. So again, you put this in a matrix. Matrix A is this, matrix B is this. You take the inverse of A times B, and what you're going to get is an answer that's going to be in terms of I1 and I2. And what you would get is negative 0.75 and negative 0.5. And what unit is this? Amps. That means that the mesh current I1 is equal to that, and the mesh current I2 is equal to that. So does that help me? Let's look back and see what we're trying to find. We hooked a test circuit, a test current up to our circuit. We shorted our other sources, okay? And we're hooking this guy up. All right, now what we found out is that once we hook it up, we know the mesh current's everywhere. We already know what this is equal to. We know the mesh current here, and we also know the mesh current here. What we're trying to find is what is the voltage drop across our source that we hooked up to the circuit. That's how we calculate the resistance, V over I, all right? So this voltage here, from here to here, is going to be the sum of the voltage across this 4 ohm resistor and the voltage across this one, because when you think about it, if you trace your finger through this resistor and through this resistor, you get back to where you started. So what we want to do is find the voltage across here and the voltage across here. And we can write all of this because we know the voltage, for instance, across this resistor is the current going through it, I2 minus I3 times 4. So let's go ahead and do that. So what we're going to have is VAB, which is what we're trying to calculate, is the voltage across that first 4 ohm resistor. So it's I2 minus I3 times 4 plus, again, the voltage across this one. In this case, since I1 is the guy coming down, it's going to be I1 minus I3. So it's going to be I1 minus I3 times 4. This is the voltage across the first 4 ohm resistor. This is the voltage across the second 4 ohm resistor. So what you're going to have here, since we now know I sub 2, negative 0.5 minus I sub 3, don't forget, I sub 3 we found early on, that's negative 1. So here, it's a minus sign, minus negative 1 times 4, plus I sub 1, negative 0.75, minus I sub 3. I sub 3 is negative 1, like this. So negative 0.5 minus a negative 1 times 4, negative 0.75 minus a negative 1 times 4. All right, so when you do all of this stuff, VAB, when you do all of this calculation here, you're going to get a nice number, 3. And that's 3 volts. So what this means is that when I hook a 1 amp source up between terminals A and B, the voltage that appears across this source is 3 volts. And since I'm supplying current into a circuit with a known voltage drop, when I take V and divide by I, I'm going to get the resistance of kind of like this whole circuit over here. All right, so R Thevenin is V over I. The voltage that we calculated was 3 volts across the circuit. The current supplied to the circuit's 1 amp. This is why I always choose a 1 amp source. So what we get is 3 ohms for the Thevenin resistance. And so the maximum power transfer is when R is equal to R Thevenin. So then R must be equal to 3 ohms for max power transfer. Now this does not tell us what power is actually delivered to the 3 ohm resistor, but what it does tell us is that we have to put a 3 ohm resistor across those terminals to get the maximum power delivered to that resistor. If we put 2.5 ohms there, we're going to get less power delivered. If we put 1.5 ohms, we're going to get less delivered. If we put 3.5 or 4 or 5 ohms, something a little larger than what we have, we're going to get less power. Only when you put 3 ohms there does the maximum amount of watts get absorbed or delivered to that resistor. All right? So you're matching the resistance of your load to the resistance of the whole network, basically. And notice we didn't really find the Thevenin voltage, even though we found VAB. See, we found the voltage across this once we had the source hooked up. We never actually found the Thevenin voltage because the Thevenin voltage would be of the original circuit. If we were wanting to find the Thevenin voltage, the way we would have done that is we would have taken this resistance out, so we exposed terminals A and B. Remember, Thevenin voltage is open circuit voltage. And then we would have had to solve the circuit for the open circuit voltage. We didn't do that because we don't want to do that. We only want to find the Thevenin resistance. So the way we do it is we take this out, we hook a test source up, we short out our independent sources, and we go and we find the voltage across our test current source. And that allows us to calculate the Thevenin resistance. Now, if you wanted to calculate, that tells us what value of resistance R needs to be in the circuit for max power transfer. But if you wanted to calculate actually how many watts this resistor actually absorbed, then the way you really should do it is take 3 ohms, replace this unknown with 3 ohms, and solve the circuit again, figure out what current's actually flowing through that resistance. And then once you figure that out, then I squared R is the power delivered to that resistor. Or once you have the Thevenin voltage calculated, you could use the equation I gave you from the very last section right before this one, where the maximum power delivered is V Thevenin squared over 4 times the load resistance. So either which way you want to go, if your question's just asking you what value of resistance do you need for max power transfer, then all you're concerned about with is finding out what that resistance is. And that's what we've done here. We found Thevenin resistance, we set it equal, that's the answer. If your question goes further and says, okay, now that you've chosen the magic resistor, how many watts is actually being delivered to it? There's a couple ways to do it. The first way would be just to take the resistance you calculate, stick it in the circuit and solve the circuit again, figure out what current's flowing through it, and then I squared R. That's going to be the maximum power delivered to the resistor. Or, if you wanted to, you could just take away the R and find the open circuit voltage. That would be the Thevenin voltage. And again, use that equation from the last section, V Thevenin squared over 4 times the load resistance. Either which way, you're going to get the same answer because they're both derived from the same set of principles. So make sure you understand this. It all boils down to being good at finding Thevenin circuits, basically. We've done a lot of problems with that for that reason. It comes in handy in lots of different applications. Make sure you can do this. Follow me on to the next section. We'll do another problem with maximum power transfer. In the next problem, we will be finding the value of the load resistance, and we'll also be calculating how much power that load resistance is actually absorbing, or how much power is being delivered from the source to that load resistance in the circuit.